Hold up. How many of you are actually here right now? I see 8. Nah, never mind. It's actually 7. One of the person is just me. Oh, no, it's 6 now. Just ask me questions if you have any. Otherwise, I'm gonna keep doing what I'm doing on my other monitor. You guys gotta use your own name. I knew it. I knew it. I had a feeling that was you. I had a I had a feeling. Do you have a question, Bestie? That's a broad topic. Can you be more specific about the gravity thing? Okay. It was the G thing. The G is 9.8. It's just the positive version of acceleration. Unless you want something more in depth than that. Um, Total mechanical energy is just the sum of both potential and kinetic. So it's all energy, all energy. So like how potential and kinetic are just two categories, mechanical encompasses both. We do work on objects when we apply a force moving at a distance. If you don't move at a distance, you're not really applying a force. What about Q? Oh, internal energy? Yeah. So total mechanical energy just yeah, so Q is included in total mechanical energy. All energy. Your total energy of your system. Bestie, did I answer you, or was that still not clear? So if you have a box, right, and you push it and you apply a force and it moves a distance of, let's say, 1 meter, you're doing work because work is force times distance. Well, if you're lifting something, you're gonna use FGD, right? Because and again, it's an oversimplification because we're using FG because FG is equal to your the applied force going up. All right, I'm gonna answer Serena's question first, and then Kalia's, so I don't get all mixed up. So Serena's question is, how do you know when to use W is equal to FGD or when to use W is equal to FD? They're not gonna give you two situations. You'll know, and we use FG because if you look at this free body diagram, if you're lifting something, you know your FG is equal to FA, right? And so your work is your force applied at distance. I just in your key I wrote it as FGD because it was easier and doesn't require a lot of explanation, right? It's a simplification. So if you're lifting something, right? If lifting because FG is your weight, FG is your weight. So you're gonna use FG when you're lifting something. Now, no, I'm not writing with mouse. Also, Serena, did I answer your question? You gotta give me a response. And now Kalia's question. So why is total mechanical energy able to increase and decrease, but energy total has to remain from start to end? Ah, okay, okay, okay. All right. So now, why is Foizel in here? He's not even in my class anymore. Uh, all right. So ET. So you're assuming ET at the top and ET at the bottom stay the same. We're assuming this is the same top, bottom. Only when no energy is added, right? On, if I don't do any work, let's say there's a ball and it falls down and nothing else is doing any work on this ball and just falls down. Yeah, my ET at the top is equal to my total energy at the bottom. But if it's somehow in the middle of its path downward, I maybe slap it with my hand, right? And this is not really a hand, sure. Uh, and I slap it with my hand, I am going to increase my total mechanical energy here, right? I'm doing something to this ball falling down. It's not falling down alone anymore. So does that make sense, Kalia? I'm not also if I'm writing something and I'm I'm not talking, remind me to use my push to talk button. And also your total mechanical energy will increase because as you go up, let's say there's friction here. Let's say there's friction here. And as I go up, I'm pushing this box and there's friction and the friction is doing work on my box. Just the test topics, Kevin. Just the test topics. And so friction is doing work on this box and so it's increasing my energy. you do not increase your total energy unless you do work, right? And so that's your work energy theorem, where W is equal to a change in total energy. All right, so you need to do work to change your total energy. All right, and now next question after Klia's of Bessie's doesn't really have a question. Am I writing with a mouse? No. Hello, everyone. Hello. All right, next question. And again, going back to the work is equal to delta ET, right? Work is force times distance. So if I apply a force and move it a distance, I'm doing work on it. Let's say, for example, this thing right here, this cart, right? This cart has a kinetic energy of 0 because it's not moving, right? It's not moving. And let's say it's on the ground. Let's say it's on the ground. My potential energy is 0 as well. So my total energy of the system right now is 0. Is 0. Well, if I if I apply a force and I start moving it this way and it moves, let's say 1 meter, well, it has kinetic energy now because it's moving, right? So my kinetic energy is not 0, it's some number, and so my total energy just increased. And so my total energy just increased because I did work on this object, right? I changed the amount of energy this object had because my work is equal to delta ET. Who the hell is Triple J 360? I have an idea. Is that Justin? But let me know if that explanation helps, or do I need to explain it in a different way? Because I'm using a pen. Okay, so right now I'm using this pen. I'm using a pad on a. It's like a tablet. I'm using a pen on a tablet, and so the pen tablet, no, the pen is acting like a pen. How else do I rephrase that? It's a pen. I'm not gonna cuss at students. Yeah, so when so let's go over Bestie's question. So and let's take this incline for example, right? And let's say you're riding a bicycle, bicycle. Actually, I'm just gonna make it a cart to be honest, because I can't draw a bicycle. But let's say you're increasing your height, right? So again, your potential energy is mgh, and so if your height increases, well, your potential energy, your gravitational potential energy increases as well. Because at a height of, let's say this is 10 meters and this is a height of 0, well, if you're increasing your height as you're going up this ramp, this incline, your height increases and your potential energy increases. And the formula for kinetic energy is 1/2 mv squared. All right, and so if your velocity increases, right, if your velocity increases, then your kinetic energy must increase as well. But let's say this car is traveling at a constant speed, right? Let's say it's traveling at constant speed. Well, if I'm traveling at a constant speed, my velocity doesn't change. I have no change in velocity. And this delta means no change, by the way. Change. Okay, so if you're traveling at a constant speed, your velocity doesn't change. If your velocity doesn't change, your kinetic energy doesn't change either. Right? Doesn't change. Because it's traveling at a constant speed. What the hell is question 8? Number 8. Let's see. So number 8 says a horizontal force, right? Force 5 newtons. So you're applying that force. So I'm calling it applied force. Mass of 3 kg. A distance of 6 meters. And what is the change in kinetic energy of this mass, right? So this again, this is going over the work energy theorem, where your work is your change in total energy. Now, I want to assume, since it says frictionless, I'm just gonna ignore that. Not that. But if it says frictionless, we know as the thing gets moved across the surface, your change in internal energy is zero, right? Your change in internal energy is zero because you're not losing anything to heat because there's no friction, because that's what the problem says. Now, well, if you're just moving horizontally, you have no change in potential energy either, because you're not changing your height. Your height still stays on the bottom. I'm actually gonna stop the stream if Wobo keeps showing. There's a fine line between joking and getting fired. I can't tolerate that. That's just that's just how it is. So okay, so yeah, your work energy theorem. Work is equal to change in total energy, and so this is your work energy theorem. So to change the amount of energy something has, you need to do work. So if I'm pushing something, I'm doing work, and I'm changing its energy. And we know that change in total energy is equal to change in PE plus change in KE plus change in Q. And so we know that you're not going up, right? So your change in potential energy is zero, and we don't know what our change in kinetic energy is. And my change in Q is zero because I have no friction, right? You're not losing any energy to the friction. And we know that my work is force times distance, right? So work is force times distance is equal to change in kinetic energy. So now I have everything we need. I have my force here, right? I have my force. I have my distance, which is 6. I have my kinetic is equal to my change in kinetic energy. And so it's going to be 30 joules is my change in kinetic energy. All right. So let's go over this again because I paused in between. Number 8. These are your knowns. You know your force that you apply is 5 newtons. You know your mass is 3. And you know that the distance you apply that force over is 6 meters. And you want to find out what is your change in kinetic energy. Now, you don't it says frictionless surface. Because it's frictionless, you can say that your change in internal energy is zero. Because you're not losing any energy due to heat. And since we're just going horizontally, you're not changing your height either. Because you're not changing your height, your potential energy, your change in potential energy is zero. So now we go to this formula right here, your work energy theorem, right? Work is equal to change in total energy. And we know that change in total energy on your reference table, change in total energy is PE plus KE plus Q. And I can't write there because something to do with it, the tablet. Uh, now, but yeah, so change in total energy is equal to change in P plus change in K plus change in Q. And we know that my work is force times distance. So all I'm doing is I'm replacing W here with FD. I'm substituting 0, right, into here, 0 from Q into there, and I'm left with that, and then I just solve. So you're basically using context clues in the question to solve the problem. Now on to Bestie's question. And you can rewind, you can pause here if you want to copy this down while I answer Bestie's question. Now, for what vertical distance is a 50, I'm going to assume that's a 50 Newton object, okay? So let's say your weight is 50 Newtons, right? Because Fg is your weight, right? You know that's another word for weight. And you do 150 joules of work. So what is the through what vertical distance? And you want to know what your distance in the vertical direction is, okay? And so we know that work is force times distance. And so it's going to be 50 over there. I substitute F with 50, and work is 150. So divide this, and I get 3 meters. All right. How are we doing? How are we doing, guys? Questions? Did I answer your question, Bestie? Did I answer your question, Andy? Was it Andy or was it Kevin? Did I answer your question, Andy? Do you understand how to do this question now? All right. I can guarantee that's. I mean, I can't guarantee it. I actually don't remember the questions that I put on the test. When I print it out tomorrow, I'll figure it out. Bessie, did I answer your question? Do you understand how to do it now? Before I move on to Andy, Andy's new question. Respect the step. Respect the step. I did I answer your question? Hold on. I mean, I'll go over it again. So your question, hello, Rowita. Your question, Bestie, is for what vertical distance? God damn it. For what vertical distance is a 50 Newton object? Okay. So your weight is 50 newtons, right? That's Fg. Okay. And your work is 150 joules. And they want to know what is the distance that your gravity does, that your gravity moves it. So you have Fg, you have W, and D. And we know that W is equal to Fd. So all I'm doing here is replacing W with 150, replacing F with 50, solving for D. So 150 divided by 50 is 3 meters. All right. So now let's move on. Number 12 in 2.14. So your mass is zero point 0.1 kg. Your tree is 2 meters. Can I release the step? Can... Okay. Yeah, no problem. Right? So your FG is 50 newtons. Right? Are we fine with that? Your force due to gravity is 50 newtons. Because that's your weight. No, no, I'm fine with doing this. I think this is should be easy. So, and it says 150 joules of work. So you know your work is 150 joules. And then and the question wants you to figure out what was your distance that you move it. And we know that my formula for work on your reference table is W is equal to FD. So your work is 150, your force is 50, and you want to find out what D is. And so you divide 50 on both sides, right? And you get 3 meters, and that's your distance. And I'm gonna leave this here while I do Andy's problem on the left hand side. Yeah, no problem. So you stretch a distance of zero point 0.1 meters, right? So the spring stretches a distance of zero point 0.1 meters from a height of 2 meters, right? The apple falls from a height of 2 meters. So if all the gravitational potential energy turned into the potential energy of the spring, what is the spring constant of this spring, right? So if we know that all my gravitational potential energy of the apple at 2 meters high turned into potential energy of the spring, that means I can just calculate for potential energy first of the apple. And so now I'm solving for my potential energy of the apple on top of the tree. So zero point 0.1 times 9.8 times 2. And I'm going to round this to 10. So 10 times zero point 0.1 is 1. And so 1 times 2 is going to be 2 joules. All right. So this is my potential energy, my gravitational potential energy at the top. And we know that once the apple hits the spring, all my energy goes into potential energy. So we can say that, well, my potential energy of my spring now is 2 joules, right? When it's compressed at the moment of maximum compression. And I'm going to erase this part now. This is taking up space. It's not a completely perfect eraser. It's going to be some things left behind. And well, now we know that, well, we also know that potential energy of my spring is equal to 1 half kx squared. And we figured out right here that my potential energy of my spring, when it's compressed 0.1 meters, is 2 joules, right? Because when the apple falls down on the spring, it's compressing it. And so now the spring has potential energy. And so now that's 1 half k. We want to solve for k, and we know that my distance that I stretch it is 0.1 squared. And so 0.1 squared is going to give you 0.0. God damn it. So 2 is equal to 1 half k. 0.1 squared is 0.01. 1 half. So 1 half times 0.01 gives me 0.05. Divide this, and you should get some number. I think that's, what is that? Just let me just look at the choice. 400, maybe. X is the how long you elongate the spring, how much you compress the spring or stretch it. Wait, never mind. Yeah, actually no, I'm right. Yeah. X is how much the spring is compressed or stretched. Right? So in the problem it says the apple falls and hits the spring, compressing it 0.1 meters. Did I answer your question, Bestie? Did I answer your question, Andy? Everything fine? Any problems? Oh yeah, someone asked me how many questions. I told you this in class. You have 14 questions tomorrow and 11 questions on Friday. They're fairly easy problems. Yeah, it's not saying much that I'm seeing it. Of course, I'm going to think they're easy, but I think they're easy. Yeah, yeah, yep, yep. Nah, too much work for me. Short response is too much work for me, to be honest. So I have to go through your responses, read them, and try to decipher them, try to figure out what the hell you guys are telling me. Your lab short responses are enough. That's enough reading for for a week. Man, some of the things you guys say. Yeah. So X is how far you stretch it. Well, regarding springs, okay? Regarding springs, X is gonna mean something else and everywhere else. So let's say your spring right here is 1 meter, right? And so that's should mean the length of your spring. And then you stretch it, and then you stretch it, and now it becomes the length of this spring right now. The stretched length is 2 meters. Never mind. Hold on. I think I'm gonna make this 0.5 meters. And so, well, then x is okay. The proper definition is for x is distance from equilibrium. Okay. So the distance from your unstretched length is 2 meters minus 0.5. So 2 minus 0.5 gives you 1.5 meters. And so that's your x. And so that's your distance. I mean, that's your x. That's what x means. I didn't want to use 1 meter there because 2 minus 1 would be 1. And maybe some people would get confused about what x meant. It's like, am I talking about the length of the spring or like the difference? And so that's why I changed it to 0.5. I foresaw difficulties. I'll tell you right. All right, let's go over the reference table. Let's go over all the formulas. So all the way at the back. All right, let's actually make this bigger. Sure. So the first two, the first two formula that deal with Hooke's laws and springs are these two right here, right? Fs is equal to kx. All right, and so if you don't know what these mean, it's all on the right hand side. K is spring constant, right? And x is somewhere. Yeah. Change in spring length from the equilibrium position. I kind of paraphrased it, made it shorter. And your potential energy of the spring is right here. And the other formulas you use are all over here, right? This is potential energy, change in potential energy, kinetic energy, your work energy theorem, total energy. Again, this total energy is only true if you're not doing work on the system. So if you're not adding any energy to the system by doing work, then this should be true, right? Your total energy at the top is equal to the total energy at the bottom. Now, and the power and work formula is down here. And so these are all the formulas. These are all things power can be, right? Any other questions? Welcome to the tutoring. Tutoring starts after the break. But I really next semester, I don't know. I don't I want to teach. I hope there's enough physics classes so I don't have to teach anything other than physics next year. It's really destroying me right now. I hate teaching anything other than physics. But please ask me any questions. I'm gonna not. I have no comment for that, to be honest. Not to say something, but decided not to. Bestie, you don't even come to tutoring. I don't know why you're asking for it. Actually, never mind. That's a lie. You do come to tutoring. I'm sorry. I just remembered. I apologize. I vaguely recall you coming now. I vaguely. You always come with Kwanje. Bestie, I can't. Okay, Q. You don't have to remember this. It's on your reference table. So Q is in most questions. Q is gonna mean your internal energy. I no, okay. In most questions, Q is gonna mean the amount of heat energy you lose. That's usually what Q means. I think if you ever use it in chemistry, Q also means something heat related. Pretty sure. But for the most part, Q is gonna be your heat energy. And if not, it's gonna be internal energy. Yeah, the glasswork one. Messi, I don't know why you act like such an airhead when you're not. I don't know why you act like this. You act like you're oblivious, but you understand what's going on. You I know you understand what's going on, but you act like an airhead. I don't think the first day is gonna be too hard. I think this, I'm looking at a test right now. I don't think the first day is gonna be too hard. Depends whether or not you guys did the homework. There's only two questions that are math heavy. And I edited the numbers so that you don't have to use a calculator to solve for them. I As long as you plug in the numbers, and that's never gonna happen. Yeah, no problem, bestie. I hope you do well tomorrow. No, nothing's happening, bestie. I'm not showing anything. I'll end the stream in 5 minutes. I think this is good. I answered a few questions. I I I never. Yeah, you can take the test again. That's always, yeah, sure. I'm never gonna teach online. I'm not spending. Never. There actually are online courses, like online classes. There are those type of stuff, but I'm not getting paid to do that. Of course, it's no. It's always during tutoring. 6. What is the rate at which work is done? Uh, Power is act. The literal definition. Hold on. The literal definition of power is rate at which work is done. Rate at which work is done. Because rate is just something over time, like how fast you do it. And we know that power is work over time, which makes sense because what is the rate at which work is done, right? How fast do I do this work? And that's my power. So we know my force due to gravity is something. We're not giving our force due to gravity, we're giving our mass, right? We're giving a mass and we want to find power. And we know that my speed is 5 meters per second. And my force due to gravity is 35 times 9.8, right? Because I don't know, I'll list all my steps. So your mass is 35, and we know that g is 9.8, and we're round this to 10. So 10 times 35 is 350. Okay, 350 newtons. So now I have my force due to gravity, and I want to find out power, and I have V. So if you look on your reference table all the way at the bottom, there are three different formulas for power, right? Power is equal to force times average velocity, and force is going to be 350, and your velocity is going to be 5. And so 5 times 350 gives you 700, 1750. 1750 watts. Is that an answer on the well, they don't say 750. The closest 1700. Good enough. Good enough. I'm gonna assume that if I didn't round it to 10 and I just used 9.8, I would have gotten around 1700. Yeah, no problem. You say that, Rowita, but you know you're gonna get 100. Don't say that, Andy. That's rude to people. The math might be simplistic, but maybe coming to the conclusion might be a little bit difficult. Yeah, so the math part might be fine, but how to solve it, like which formula to use, like knowing that rate at which work is done, reading the problem, reading the problem is a bit might be difficult for some. Once you figure out how to solve the problem, it's pretty much you pretty much got it. And that doesn't say much because yeah, once you figure out how to solve the problem, obviously you've finished solving it. But what I'm trying to say is that once you know what the problem, once you, I'm gonna stop. No, I was mistaken, Rita. I was looking it up because I was curious because it's been a while, and I never really cared about proving the formulas either. I mean, I never cared about proving the formulas myself. Uh, which is commendable that you're actually trying to prove it. I don't think I ever had that mindset when I was in high school. But I looked it up, and you're actually supposed to use Newton's second to prove energy. You're supposed to use Newton's second. The reason why I said conservation of momentum is because that still has something to do with conservation of energy, right? There are some collisions where energy is conserved as well, and then where energy is lost. So that's why I said conservation of momentum. I was mistaken. Was mostly on the test? You know what's on the test. I tell you what's on the test. Google Classrooms. You can assume that it's an even split, okay? That's what you can assume. It's an even split among the days, among the topics. So let's say there are 14 questions on the first day, and there are 3 topics. Divide 14 by 3. You get 4.6 as your average question. I don't know, I'll link you a video of the proof of this. I mean, the proof I'm linking is done by calculus. You're asking the wrong person, Rita. I know that the I know that the formulas are proved using calculus, but I was never asked to prove these formulas, and I never cared much to prove them myself. I I'm actually just googling it right now. That's what I'm doing. Let's see if I can Google it in the next minute. And it's using calculus. Yeah, this is it. I mean, okay, so that's a work energy theorem. Then once you figure that out, yeah, never mind. Kinetic energy is done from Newton's second. A lot of things are actually done from Newton's second. That's kinetic energy. Then you can pretty much work from there and solve and do potential energy. All right, I'm out. It's 8. Thank you for. I hope I answered questions. Goodbye.